Okay, welcome everyone. And today we are going to have this seminar that's about 40 minutes of the talk, followed by the question and answer up to 20 minutes. And let me first introduce the speaker. And Katherine Irimata is a math statistician at the National Center for Health Statistics in the Division of Research and Methodologies Calibrating Center for Statistical Research and Survey Design. She received her PhD in statistics from Arizona State University. Her research at NCHS has included work on correlated data, segmented regression, and survey methods. Katherine's primary focus is on NCHS research and development survey, a series of web-based commercial survey panels, including conducting methodological research on the estimation and calibration weighting for panel surveys. Okay. Katherine will pause and from time to time for clarification questions during her talk. So you are free to pose any clarification questions during the presentation. Please leave your discussion questions at the end of the talk, okay, at the end, and then we can focus about 20 minutes just for question answers for discussion, okay? So without further ado, let me pass the stage to Katherine. Okay, so Katherine, you are free to share your slides and start your talk.
Thanks so much for the introduction. I'll share my screen. Thank you, everyone. For joining us today. I'm so glad to see the interest, and I'm looking forward to speaking with you about this topic, which is just talking about estimation from web-based surveys. I say just, but there's a lot to it. So thinking about how to choose the right variables to reduce selection bias in our estimates. So as Yan mentioned, I'm at the National Center for Health Statistics, and I wanted to start off this talk just giving a little bit of background and motivation for this research. I think someone's drawing on the screen. One second. Can everyone see that?
Yes.
It's okay now, yeah.
Okay, thanks. So yes, I'm at the National Center for Health Statistics, and NCHS is the United States principal health statistics agency. And so our agency is responsible for monitoring the health of the US, and we do this through various surveys and data collection systems. One of our more recent surveys is called the Research and Development Survey. And as Yan had mentioned in the introduction, this is an ongoing series of surveys that's conducted by NCHS within the Division of Research Methodology. So RANS is primarily recruited, so probability sampled, web-based commercial survey panels. And although they've been primarily probability sampled, we have had some non-probability surveys as well as some phone respondents. And RANS, unlike other surveys where we actually publish estimates, it's designed to expand NCHS's methodological research program. And so there's really two primary goals with the RANS program. The first is to supplement NCHS's survey and questionnaire evaluation efforts. And this includes looking at measurement error in our questions. And the second is to explore ways to integrate data from commercial survey panels with high quality data collections to produce reliable national estimates. And this is the primary focus. Looking at estimation is what we're thinking about in the talk today. And I just want to mention that although RANS was designed for methodological research, it was adapted to provide early experimental estimates. And so we did publish estimates from it related to the COVID-19 pandemic. And I provided the link here in case anyone's interested in looking at that. So focusing on that second goal of the RANS program, we're really interested in producing reliable national estimates. RANS has many benefits, including the capability to collect data quickly, and it's less costly than traditional national household surveys. However, RANS is subject to potential bias because we have lower sample sizes, potential coverage bias, and higher non-response bias than our other household surveys that are conducted at NCHS. Adjustment methods have been used to construct pseudo weights or an adjusted weight in order to balance the covariate distribution in RANDs to higher quality benchmark data sets in order to reduce bias in our national estimates. And these adjustment methods have included propensity score-based approaches, which I'll discuss further in this presentation, as well as raking. And so a key question that's come up during this research is when we're constructing the adjusted RAND weights, how do we select the variables that we need to include in our weight adjustment? Should all variables be included in the adjustment, or are there only certain types of variables that are needed? And so this is really the motivation for this work that I'll be talking about today. Ideally, we'd like to know how do we select the variables that we need to adjust RAND weights. We'd like to improve our estimates that come from RANDs by reducing selection bias. And then finally, we'd like to prepare for future surveys. So if we can identify the variables and the topics that are important for survey weight adjustment, then we can make sure that those are included in our future questionnaires. And so this talk is going to focus on the research performed on how to choose the right variables for adjusting survey weights to reduce selection bias in RAND specifically, but also more generally in surveys that can be impacted by selection bias. And so this includes web-based surveys as well as non-probability surveys. So I'll start off giving some background and methods. I will discuss a simulation study that was done to demonstrate the recommendations from this research. And then I'll look at an application from RANDs. And so for the application, we're going to look at estimating national prevalence of asthma in 2019, and then wrap up with a discussion and just a few practical guidelines. As Yan mentioned at the beginning of the talk, I will pause a few times throughout the presentation to see if there are any clarification questions in the chat, but otherwise I'll take most of the questions and we can have any discussion at the end. So the motivation for this research came from the RANDs platform. However, these types of questions are generally applicable to web-based surveys. Web-based surveys, like I described for RANDs, can be used for more timely and cost-effective data collections, which are really beneficial. But we do know that they're subject to lower coverage and response rates than large, nationally representative surveys. And selection bias has been a particular concern due to differences in the composition of web panels compared to the total population. So for example, for some web panels, it's been seen that panel members might be more educated or have a higher income compared to individuals who don't participate in panels. And in addition, there's been concerns about the accuracy of estimates related to disease incidence because individuals who participate in panels might be healthier or have lower disease incidence than those are sicker and wouldn't be able to participate in the panel. So one approach for adjusting the weights for web panels so that they more closely reflect the total population is through the use of propensity score methods. So propensity score methods were developed by Rosenbaum and Rubin to control for confounding in treatment estimation in observational studies. And this often comes up when we're talking about causal inference. However, propensity score-based methods have been used in survey research, and it's been used as a re-weighting method to adjust the weights for the surveys. Propensity score methods for the survey application, use an existing high-quality probability sample as a reference to align the distribution of the specified variables between your target survey, which in this case, we're looking at web surveys, and the reference survey. And the estimated propensity scores then are incorporated into your weights using various approaches. And so, for example, propensity score weighting and propensity score matching are two main approaches that are used. Propensity score matching directly uses the estimated propensity scores to adjust your weight. So, for example, you could divide your survey weights by your propensity score by a function of the propensity score. On the other hand, propensity score matching uses the estimated propensity scores to match similar responses. And so you need a specified distance measure to determine what's more similar, to determine similarity. And then the matched responses will be adjusted accordingly. So bias prediction, so even after using the propensity score method to adjust your weights, the bias reduction really depends on the outcome and the variables that are collected in both the target and the reference data sources. And so this includes covariates that may not have been collected. So the effectiveness of using a propensity score adjustment method really depends on identifying, not only identifying the proper set of covariates, but we need to have those covariates available. And it also matters what the quality of the data is that's been collected. Literature generally recommends including all variables in a propensity score adjustment. So this would be any variables that are overlapping between the target survey and the reference survey. However, we're interested in identifying specific types of covariates that are critical for collection in order to improve the validity of our population estimates. And as part of this research, we use a directed acyclic graph, or DAG, to examine how different types of variables and causal pathways impact the performance of the propensity score adjustment. And so next in this method section, I'll show these DAGs to give you a sense of how the covariate relationships, what the covariate relationships look like for this type of problem. So to get started, these are the variables that we'd be considering when we're thinking about performing a propensity score adjustment. So the first is our outcome of interest. So this is important. What variable do we want to produce the population mean, or estimate the population mean for? And so, for example, later we'll look at an example from RANDS with asthma. And so this may be our asthma outcome, like whether someone's been ever diagnosed with asthma. We also have a selection indicator for our target sample. And so this is whether or not someone was participating in the web survey or reference survey. And so this gives us a sense of differences we might see between respondents who respond to web surveys versus our general population. We also have variables that are related to both of the outcome and the selection indicator. And so we'll call these confounders, and will be represented by X1 for the presentation. And so, for example, if we're thinking about the example of asthma, a possible confounder just based on the literature search might be race and ethnicity. We see that asthma prevalence varies by race and ethnic groups. And we also see that web survey participation may vary by race and ethnic groups. Another type of variable would be our what we'll call outcome predictor. And so these are variables that are related to the outcome, but aren't related to the selection indicator. And so for this asthma example, something like smoking might apply. We could think that either someone who smokes or who is exposed to secondhand smoke might be more likely to have asthma, but smoking may not be related to whether or not someone participates in a web survey. And then the final type of variable that we'll be thinking about are selection variables. And so these are variables that are related to our selection indicator, but not to the outcome. And so this could be something like internet access or even age. We think these variables may not be related to asthma, but they could be related to whether or not we expect someone to participate in a web survey. So here is an example of a DAG. And so we can display the covariate relationships that I just described using this graphical tool. DAGs were developed for causal interpretation, but in this case, we're not interested in the actual causation, but we want to understand the covariate relationships that exist. And so here we can see that we have our outcome, Y, and sampling indicator A, as we've described. And then we can think about the different types of variables that are associated. So confounders are related to both, outcome predictors are only related to the outcome, and then selection variables are variables that are only related to the sampling indicator. We could also think about maybe a fourth type of variable that's not related to either our outcome or sampling indicator, but in this case, those won't be important since we wouldn't need to adjust for them. So we want to understand how the inclusion of certain types of covariates, like the ones that we just described, including those in the propensity score model will impact the bias. So it's the difference between our estimate and the true population value, and the variance of the sample mean from our target survey, our web survey. And ideally, we'd like to select covariates that result in little to no bias in our sample mean, because that's our estimate of our population mean. And we'd like something with low variance. So the numerical evaluations of the bias and the variance of the sample mean aren't provided in this presentation, but it can be shown that the conditional distribution, when the conditional distribution of A, our selection indicator, given Y, our outcome, is the same as the distribution of our selection indicator A, that the bias will be 0. So it can be shown that when the covariate is independent of our outcome, so something like our selection variable, X3, or the predictor, which we're calling X2, that the two distributions will be the same and so that we won't have bias. But when the covariates correlate with both our selection indicator and the outcome, so that's our confounder variable, X1, then we won't have bias that's equal to 0. And so in that case, it's important, we'll need to balance the distribution of the confounders, our X1 variables, between the target sample and the population in order to have unbiased estimates. Similarly, when we're evaluating the variance of our sample mean, we can compare the variance of the means when our weights are adjusted by propensity scores that are calculated using these different variable types. And it can be shown that the inclusion of selection variables, that's that X3 variable, will result in larger estimates. And I think intuitively this makes sense because selection variables are independent of the outcome. They're only related to the selection indicator. And so propensity score adjusted weights that are based on these selection variables aren't going to be informative of our outcome. And so including selection variables don't add bias to the mean estimate, but we will lose efficiency. Another situation that we should consider is when we have correlation between covariates. So that first DAG I showed you only looks at relationships on the different, how the different covariates are related to our outcome and our selection indicator. But in practice, these different types of variables can be correlated to one another. And the DAGs shown at the bottom of the screen show different potential relationships that could exist when we have correlation between, for example, our confounder and our selection variables in the first graphic. So any pairs of the variables as shown in the different pictures below, or all variables could be correlated simultaneously in the underlying population. And so it's important to understand how this can impact what variables we need to include in the propensity score model. So for unbiased estimation of our population mean for our specified outcome, so for example, asthma, when we using the web survey or our target sample, if we have correlation, we're going to need to block or prevent information from flowing between the paths that connect A, our selection indicator, and Y, the outcome, because we want the conditional distribution of our outcome given the target sample or given the selection indicator to be the same as just our distribution of our outcome. So we can do this using the backdoor criteria described by Pearl. And so we're going to need to remove confounding by conditioning on the set of covariates that will block those backdoor paths. So there's 3 scenarios that are shown at the bottom of the screen. The first one shows correlation between our confounders and our selection variables. So that's the X1 and X3. The second shows correlation between confounders and predictors. That's our X1 and X2. And then the third one shows correlation between the predictors and the selection variables. So it's X2 and X3. In all of these figures, the dotted lines are identifying the paths that need to be blocked in order to have independence of A. So in the first and in the third graphics, there are 2 paths that need to be blocked, shown by the blue and the red dotted lines. And then in the second graphic, we see that there's just one path that will need to be blocked, which is from the red dotted line. So if we look at each of these scenarios, for the first 2 scenarios, adjusting the distribution of our confounders, so those X1 variables, will be enough to block those paths so that we have independence between A and Y. But in our last scenario, when we have correlation between the predictors and the selection variables, we actually need to adjust the distribution of the confounders to block that path from X1, as well as one other variable type. So we're either going to have to adjust for the predictors, which are our X2 variable, or the selection variables X3 to block both of those paths. And so I think it can be kind of confusing to think about all these different variable types and the different variables, but I think the summary from these, the takeaways is really, first, in the simple case, propensity models should include confounders. So those are variables that are related to both the outcome and the selection indicator. And so either just the confounders by themselves or the confounders and outcome predictors. So any variables that are related to the outcome of interest in order to produce unbiased and efficient mean estimates. Generally, including selection variables, these are variables that are only related to whether or not someone participated in the web survey or the non-probability survey and aren't related to your outcome, won't add bias, but it will inflate the variance of your mean estimate. In the case where you have correlation, it's important to see what covariates are correlated. So if it's the case that your confounders and your predictors or your confounders and your selection variables are correlated, then the confounder should be included in your propensity model in order to produce an unbiased estimate of the mean. And if it's the case that you find that you have correlation between your selection variables and your predictors, or all of the variable pairs are correlated, then you're going to need to include the confounders as well as another type of variable. And so that could be your predictor variables or your selection variables. And so you'll need these pairs included in your propensity score model in order to produce unbiased estimates. I'm going to pause there for a second just to check the chat to see if there were any clarifying questions before moving on to the simulation. Okay. All right, so let's look at some simulations to see the setups and get a better sense of what improvement we see when we include these variables in the propensity score model. So we considered a simulation. So the simulation setup, we generate a population of the true population of our data, and then we're going to sample to create our target or web sample, and then our reference probability sample to do some estimation with using propensity score modeling to adjust the weights. So the first part is to set up our population. So we had a population of size 20,000. And we just look at 3 covariates, but the covariate types are the same x1, x2, x3. So our confounder variables, our predictor variables, and our selection variables. And these are simulated using a trivariate normal distribution. And we can specify the pairwise correlation. So in the simplest case, we can consider uncorrelated data, which was that first DAG that we looked at. And then later we can vary the correlation between those to see the impact. So we created a binary outcome, y, which has the mean here. And I think the formula is not so important, but as I just want to point out primarily that you can see the mean is generated so that it only is related to x1 and x2. So that's the confounder variable and the predictor variable. So no variables that should be related to just the selection indicator are included here. So we can generate it so that we have an interaction or no interaction between these two variables. So once we have our population simulated, we can actually draw that target sample, or what would be our web sample in this example, and then the probability sample. So the target sample has a sample size of 1,000, and we can select it from the population using probability proportional to size sampling, to PPS sampling, with a specified measure of size. And again, not focusing on the equation so much, but seeing that it is dependent on our x1 variable, so the founder. So these variables were associated with both selection into our sample as well as creating the outcome. And then the variable x3, which is going to be our selection variable. So it's only related to inclusion in the sample. In this case, because we're working with, this is considered our target sample, and we know that we have some selection bias, we're actually going to ignore the sample weights. And so we're going to treat them as unknown, even though we use PPS sampling. And so these will just have equal sample weights of 1 for our simulation study. So this would be equivalent, similar to using as if we're evaluating a non-probability survey. Then our probability sample, which is our gold standard reference survey that we would be using to compare how well our target sample, the estimate from our target sample compares. We draw this with a sample size of 500. So in this case, our probability sample actually has a smaller sample size than our web survey, which can happen, especially when you're working with non-probability surveys. That could be the case, but that's not always true, and it's not the case with RANDs. And we use the same sample design. And in this case, we keep the selection probabilities. We use those as our, to generate the weights. And so we know the true values from how we sampled. And then we consider a few different simulation setups. So for the first simulation, we'll look at just independent covariates in our population. So we don't generate the data with any correlation between our covariates. And so just to look at that base case that I presented earlier. The second simulation will vary the correlation in our population. So if we know that we have correlation between any 2 pairs of variables or all of them, to see what impact that has when we need for what variables we need to put in the propensity score model. And then the third simulation, we're actually going to include interaction terms. And so those are interactions between our confounder variable and our predictor variable and the creation of our outcome, and then between the confounder and selection variable, and the related to how we sample for our target sample and our reference sample. And then we will compare the mean estimates using two different propensity score approaches, which I haven't focused too much on in this talk. So the first simulation is looking at just the basic case where we don't have any correlation between the covariates. The table here shows the results from the first simulation. You can see that for each of the, we have the bias, empirical variance, and mean squared error reported in the rows. And then across the top are the different propensity score models that were fit. The first one, the sample, is just the mean that comes from our target sample, or in this case, it's a nonprobability sample. So it's just the unweighted mean from our data. And then we're comparing that to our reference survey. This would be as if, for example, we're using the estimate from RANDS and we wanted to compare it to the reference survey there and then didn't have any adjustment. Then the other ones across the top all are after propensity score adjustment. So for example, the first one, the second column says it's WX1, and so that means that a propensity score adjustment was used, which only included the variable X1, which is our confounder variable. And then you can see we have the models that included only X2 and X3, and then we have combinations of two pairs of variables. So the first thing that we'll notice is that the propensity models that included the confounder, so all of the models that included the variable X1, produced approximately unbiased estimates of our population mean of Y. And so these columns are highlighted in that light gray color. And so you can see that compared to the sample, which these are all multiplied by 100, but the sample had a bias of 4.61. After we used a propensity score adjustment and included that confounder variable, so the variable that's related to both the outcome and to selection into our web sample, that the bias is nearly eliminated. It's very, very small. On the other hand, if we look at the columns that aren't highlighted, so when we used a propensity score adjustment that only included predictor variables or selection variables, that the bias really wasn't reduced. The second finding is that the propensity models that contained the selection variable, so that's that X3 variable, resulted in inflated variance estimates. It's not a huge difference here, but you can see that the variance estimates are larger for models that included X3. And then among the unbiased estimators, so there's the three columns that are highlighted, so we resulted in unbiased estimates for all of these that contained the confounder variable. But we see that the model that contains the confounder X1 only without any other variables yielded the most efficient estimates. And from the earlier discussion in the methods, because we have uncorrelated covariates, we would expect that we only needed the confounder to reduce bias in this case when we use a propensity score adjustment. In the second simulation, we now are going to introduce correlation. And so you can see, I only show a subset of results here, but in the first section of the table, we specify a correlation of 0.6 between X1 and X2. So that's our confounder and our predictor variables. And the other pairs of covariates are uncorrelated. In the second section of the table, we're going to set a correlation between our confounders and our selection variables, so X1 and X3 of 0.6. And then in the last section of the table, the correlation between our predictors, which is X2, and our selection variables X3 is going to be set to 0.6. And so similar setup to before, we can see the bias, empirical variance, and mean squared error reported for each of these scenarios. So again, the sample in the first column is going to be our unweighted mean. So this is the mean just coming from our target sample or our web survey without any adjustment. And then we have the different propensity score adjusted, the estimates using the propensity score adjusted weights across the top. The light gray highlighting again shows the cases where we end up with very minimal bias. And so we can see the bias for the sample is around 7.3, 7.5. After we include these propensity score adjustments, in some cases, we get the bias down to about 0.3, 0.26, again, adjusted by 100. One of the key findings you'll see is that earlier we had shown that, that if there is correlation between a confounder variable and any other type of variable, so confounder and predictor or confounder and a selection variable, which is shown in these first two segments of the table that including a confounder only in the propensity score adjustment is sufficient for reducing bias or for producing unbiased estimates. And we can see that that's true. So in this section here, we see unbiased estimates, and in this one here, we also see very low bias. But in the case where we have correlation between our predictor variable and our selection variables, so that's x2 and x3, including the confounder variables alone is not enough to reduce the bias. And so you can see we still have bias here. But when we additionally include with the confounder a predictor variable or a selection variable, we nearly eliminate the bias. And so it's very small here. We also notice that similar findings related to the variance estimates as before. And so we find that models that include the selection variables, those x3 variables, will tend to have a larger variance than models that exclude them. So even between, if you're looking at the columns that include, with propensity score models that include the confounder and predictor variable, or the confounder and the selection variable, that the model that includes the selection variable along with the confounder will have larger empirical variance estimates compared to the model that just has the confounder and the predictor variable. We can see those across the table. And so these are some of the results that I just reviewed, but generally, even though only a subset of results are displayed, we see really consistent results across all of the simulation conditions, really emphasizing that when we have correlation, it's important to check which covariates have correlation, because that will impact what the best variables are that need to be accounted for in the propensity score model. And then finally, for the third simulation, so this third simulation, the results aren't shown, but just to give you a brief overview of the results, we included an interaction term. So the true relationship in our data has an interaction between the confounder and predictor and the confounder and the selection variables. And we want to look at the mean estimates when we're using two different approaches. And so the first one is a propensity score weighting approach. And this is called, we'll call it adjusted logistic propensity, or ALP. And this is using the inverse of our participation rates estimated from the propensity model. And we'll use that as our pseudo weights or adjusted weights. The kernel weighting method, KW, is a propensity score matching method. And so that's actually going to use the matching procedure that I described earlier. So when we use the ALP approach, which is the weighting approach, we see that we have unbiased estimates only when the true propensity model is specified. And so the true propensity model, because we have interaction terms, has to include both the confounder, it includes the selection variables, as well as that interaction term between the confounder and the selection variables. So for the ALP approach, which was using weighting, it only yielded unbiased estimates when the correct model was specified, including the interaction. On the other hand, the KW approach, which is our matching method, gave us unbiased estimates across all the propensity models that were evaluated. So we looked at ones that were containing both the confounder and the predictors, the confounder and the selection variables, and then we looked at each of those with and without the interaction term. And so the KW method is, because it's a matching method, it is expected to be more robust to model misspecification, since we're not exactly adjusting the weights based on the propensity score method. And so this is while brief, I think this is really important for thinking about what methods are used for incorporating the propensity scores into your data, since the KW method and in general matching methods will be more robust. And so if your model's not specified correctly, then you can still get unbiased estimates. However, under the true model, so when it was correctly specified, the bias for the ALP estimates, so that's using the weighting method, were consistently closer to zero. And so we did have lower bias, but only when the model was correctly specified when using the weighting method. Okay, and then going on to our second to last section, so looking at application. So as I mentioned earlier in the talk, all of this research was really motivated by the RANDS program at NCHS. And so now we'll look at an example where we apply these findings to the RANDS data. So we'll take a look at data from the third round of RANDS, or RANDS 3, and this was collected in 2019 using NORC's Amerispeak panel. The panelists were surveyed using web-only administration on the survey and asked various questions related to general mental health. We have information on medical conditions, chronic conditions, opioid use, and pain. And we also, as I mentioned, will look at asthma, which was a variable on that survey. The RANS3 does have sample weights, and these are developed by using the inverse of the probability of inclusion in the Myers-Briggs panel. And they're subject to non-response adjustment and post-stratification adjustment to external population totals. So we do have some weights which we'll use as our baseline for evaluating RANS along with the propensity score adjustment. So looking at the prevalence of ever having asthma among adults, we're interested in seeing how well this compares to a reference survey. And so for the reference, we are going to use the 2019 National Health Interview Survey. The NHIS is a cross-sectional household interview survey that collects information on a broad range of health topics. And it's a very reliable survey. This is evaluated as our gold standard. And generally for the RANS program, the NHIS is used as our comparison source for looking at different estimates. And so the table here below shows a comparison, just brief comparison of RANS3 versus the 2019 NHIS. So looking at sample size, the NHIS has a much larger sample size compared to RANS. And the NHIS is conducted over the full year. RANS was conducted in about a month time span. The NHIS has a higher response rate, about 59%, rate 18. And looking at asthma prevalence between the two surveys, we see a difference. So this is the percent of adults who have ever been diagnosed with asthma. When we use RANS to produce our national estimate, we get an estimate around 16.9%. But from the 2019 NHIS, we see an estimate of about 13.5%. And so we're interested in looking at how we can adjust the RANS weight so that we can get an estimate with lower bias for asthma prevalence. So in order to adjust for this bias in our estimate, we're going to use propensity score adjustment, like I mentioned, and we'll construct these pseudo weights or these adjusted weights using the NHIS as our reference data set. So we can identify all the common covariates that exist between RANS3 and 2019 NHIS, and we'll consider these as potential calibration variables. And these include a range of sociodemographic and health-related variables. So using these looking at these different variables, we will assess bivariate correlations on our weighted data to see if we have any correlation we need to be aware of. And we found that all of the variables we were looking at had statistically significant correlations. So when we set up our propensity score model, we want to make sure that we're not only including covariates that are related to both our outcome, asthma, and involvement or participation in RANS, but we'll need to include another variable type as well. And then just before getting started, we also normalized our survey weights for both data sets to respective sample sizes, so they're on a similar scale. So thinking about the, I said propensity score model, covariate selection, it's really thinking about variable inclusion. We need to identify the covariate types. So earlier in the simulation, we were able to control which variables were confounders and predictors and selection variables. But when working with real data, we need to identify the different types. And so the way that we did this was using two different models, an outcome model and a propensity score model. And we used backward selection on both of those models, which contained all our main effects for the common covariates between RANS and the HIS, as well as the pairwise interactions for all of those variables. And so we used logistic regression models to look at these, but accounting for the complex survey design and the method. And so then using backward selection, we just removed interactions that had p-values over our threshold of 0.05, and we continued to refit it until we had our final model. And so once we had these two final models for the outcome and the propensity score model, we could identify the variable types as described here. And so confounders were common terms that were in the final models for the outcome model and the propensity score model. And then selection variables and predictors were identified as the variables that were in only the propensity model or only the outcome model. And so this is really, rather than just relying on literature to identify these covariate types, we use this data-driven approach for identifying them before actually estimating the mean and using propensity score model to adjust our weights. And so here are some of the propensity score models that are fit for comparison. There's a few different ones here so you can see the impact that it has on the estimate of asthma prevalence in RANDs compared to the NHIS. So the first one is this model.all. So this is our full propensity model. This includes all common covariates between the two surveys and the pairwise interactions. And so this is, for example, what literature would recommend that we use. We should just include all possible variables that we have and don't need to select between those variables. The second one is our model.x1. And so this one's only going to contain confounders, which we saw earlier from our simulations. Because we have correlation between our outcome predictors and selection predictors, we wouldn't expect we might see some bias reduction with this method, but we wouldn't expect it to do the best bias reduction. And this one has a couple of different options. You can see there's a .n abbreviation where it means that the outcome model is fit on the NHIS, and then .r where the outcome model was fit on RANDs. And so depending on what data set we used for fitting the outcome model to determine the covariate types, we can have some differences. The model that ends in .n means that the outcome model was fit using the NHIS data, and this would really be preferred because NHIS is our gold standard, and we want to make sure we're using the covariate associations that are present in the underlying population. But I think it's important to also think about this model that ends in .r for fitting on the RANDs data, because if it's the case that our reference survey data isn't available, or more commonly, our outcome of interest isn't collected in your reference survey, you may need to use your web survey or non-probability survey data to evaluate the different covariate types. And then we also look at models that contain our confounders and outcome predictors, and then the confounders and selection predictors. And so the full set of results are shown here in this table. You can see on the rows are the different estimation methods or propensity score models that were used. And then across the top, we report the coefficient of variation. So looking at a measure of just variation in our weights, the relative bias. And so this is compared to the NHIS asthma estimate. And then we have the standard error and the mean squared error for our estimate. So the first line reports using the original RANDs weights. So this is our panel weights from RANDs without any adjustment. And you can see that compared to the NHIS, we have a relative bias of 25%. When we use a propensity score adjustment to adjust the weights and include all possible variables, so this was all of our main effects and all pairwise interactions, as recommended by literature, we can see that we do have an improvement in the estimate. So our relative bias decreases to about 17.6%. So it is an improvement when we use all variables, but it's not the best improvement in bias that we can have. So when we only select variables, such as the confounders or the confounders and predictors, we see that we have an even larger reduction in bias. So now the relative bias drops to about 11 to 12%. Because it's not zero, this is probably telling us that there's still other factors that are not being accounted for, which we need to, perhaps there's topics or variables that aren't currently being collected in RANDs that needs to be adjusted for. But yeah, we can see a much better improvement in bias. We can also see generally the model that had the lowest relative bias was the model.x12.n. And so this is the model that contains confounders and predictor variables. And the predictors were identified using the NHIS data, which would be our true underlying covariate that contain the true relationship between covariates that we would expect from our population. And so this is just highlighting some of the observations we walked through. Generally, we did see that we had really good bias reduction when we include this propensity score adjustment, and we could further think about different variables to include. All right, so just to wrap up briefly with the discussion, then we can turn it over to questions and further discussion. So generally, the findings for the study is first, confounders, so those are variables that are going to be related to your outcome of interest and your selection indicator, are the most important variables to include in your propensity score model. If you don't have correlation, just including confounders is sufficient for reducing bias. In the case where you have correlation between your covariates, your propensity score model needs to balance the distribution of the confounder alone or of the confounder with an outcome predictor selection variable, depending on what correlations exist in your data. And just generally, the inclusion of selection variables, so variables that are only related to whether or not someone's participating in the survey, is going to inflate your variance of your population mean. And this has a few important implications. So the findings, first of all, provide a principled approach for selecting covariates for the propensity score model for estimating your population mean. So rather than including all the variables or just selecting certain demographic variables or other types, other selection methods, we're really assessing covariates based on their type and their association in the data to select that way. The study also demonstrates important attributes to collect through web surveys with specific research questions in order to reduce potential selection bias. And so this is really important for survey practitioners who are designing survey questionnaires and thinking about what topics need to be measured or collected. And then this can also be considered for future development of our reference surveys because it can be used to collect additional covariates in order to adjust web surveys or non-probability surveys. And this has currently been done with NCHS's National Health Interview Survey, which has been the reference survey for RANDs. A couple of limitations just to note. The first is that this research was really conducted with a single outcome of interest in mind. And so if you're interested in looking at multiple estimates of the mean, I think there's additional research that needs to be done on which variables need to be included in your adjustment, in the propensity score adjustment. Also, the simulation, the third simulation, which we really just touched on briefly, looked at the case when the propensity score model was misspecified. And we saw that generally propensity score matching methods perform well, even when the model is misspecified. But the propensity score model can get a lot more complicated than we looked at. So we just had an interaction term, but you can think about propensity score models that actually have higher orders of nonlinearity or non-additivity. And so it's possible that a non-parametric modeling method, rather than using logistic regression to estimate our propensity scores, can be preferred. And then this research was really on assessing the impact of bias and variance of our Horvitz-Thompson estimators related to covariate inclusion strategies, but you could think about alternative estimators where you'd want to use a propensity score adjustment. All right, so I'd like to thank you all for having me today. Thank you so much for the Washington Statistical Society for organizing this seminar and inviting me. I also want to acknowledge my collaborators on this research. So Yan Lee, who's the hosting today's session, was a lead on this research. And a special thank you also to Yule He and Jennifer Parker at the National Center for Health Statistics who collaborated on this work. I just wanted to mention that we have a forthcoming publication in the Journal of Official Statistics. And so that should be published soon. You can get additional details on some of the technical work and the methods. All right, so with that, I'll stop sharing my screen and then I'm happy to discuss any questions. And please feel free to reach out to me. You can contact me via email. There's any questions after our discussion.
Great, thank you, Katherine. And that's a great presentation.
Thank you.
We do have a question from Phil. Do you like to address that? Where you measure correlation between variables, are you looking specifically at the linear correlations? Might there be advantage to checking for nonlinear relationship? Or would that add complexity for not much benefit?
Yeah, Phil, thank you for your question. So when we were looking at correlation, it was really, just the bivariate correlation between each pair of covariates. And I didn't talk about this too much, but in the simple case, we're looking at the simulation really just had three variables, right? Just one confounder, one predictor, one selection variable, and we looked at those. In our real data, we can have, tens, 100 confounding variables and many of the other types of variables. And the way that we were evaluating was just looking at the pairwise correlations for all of these different types of variables. It's possible that there could be an advantage of looking at some nonlinear relationships. I think probably that's more important when you're thinking about the relationship of your covariates to your selection indicator. So how covariates are related to whether or not someone would participate in a web survey or understanding differences between them and the overall population. I think my recommendation is, in most cases, it's probably appropriate just to assume that you do have correlation between some set of variables in your data because there's so many variables you could look at. And so just automatically include your confounders and one other type of variable.
Okay, great. Yeah, we got another question from Charlie. Thank you for the great presentation. Doing back to your models, can you explain why variables in RANDs but not in HIS are considered selection variables? Are you using this to indicate the selection in RANDs?
Yeah, so the selection variables are ones that are related. I think it gets a little bit confusing. So the selection indicator is really a binary indicator determining whether or not someone participated in one survey or another. And so, for example, for RANDs versus NHIS, we might have an indicator 1 that the data is actually coming from a participant from RANDs versus 0, the participant was responded to the National Health Interview Survey. So this selection variables are related to actually both inclusion in RANDs and NHIS. It's describing the differences between people that respond to the two surveys. So for example, if we see that our web survey, the respondents tend to be very young and don't represent the general age distribution of the population, then age might be a selection variable because it's related to that difference. But it is talking about selection into RANDs, but it'll account for differences between the two surveys.
Thank you. From Jason, do you envision generating separate adjustments for each outcome and creating multiple sets of outcome adjusted weights?
Yeah, Jason, I think that's a really important question, especially when we think about RANDs and our goal to look at many different outcomes. So that would be one option, is you could create a separate set of adjusted weights for every outcome that you're looking at. And that way you're making sure that you're only selecting, your predictors are truly related to that one outcome you want to estimate. It does get a little bit burdensome, I think, if you're trying to estimate many different outcomes and developing all of these different weights. And so I guess my vision would be, hopefully there would be a good way to kind of choose a good set of covariates that could be used for many different outcomes. But I think that really needs further investigation.
Thank you. And Vlad asked, can you explain again why including just the confounders is not enough?
So in the case where we don't have correlated data, just including confounders is sufficient for reducing bias in our estimates. But it gets more complicated when we have correlation. So when we have correlation between our predictor variables and our selection variables, it's almost, if you're thinking about the DAG that had the dotted line connecting those two variables, we have information flowing from our outcome into the selection variable through the correlation between those different types of variables. And so we want to be able to adjust. So we want to block that information from coming through. We're going to adjust for that confounder, and confounder, it's a confusing term in that case. So we want to be able to control for that information so that the outcome and the selection variables are independent from one another. And the way that we need to do that is by balancing the distributions of one of those other types of variables to prevent that information from flowing through.
Yeah. Any further questions? Oh, we got another one from Raphael. These results seem to be in line with Little and Sonia's work back in the 2000s, in which they found that it's really important to select covariates correlated with the survey outcomes. If that's the case, do you think the variable selection could focus only on the outcome models rather than also look at the selection models?
Yeah, no, that's a great question. So if we have the case where our covariates aren't correlated, we can absolutely just focus on the outcome model and think about variables that are associated with our outcome. But as we found through our simulation study, in the case where you have that correlation between your predictor variables and selection variables, so variables that are related whether or not someone participates in the web survey, in that case, if you ignore some of the other types of variables, you will still have bias. So you'll see a reduction in your bias by including only, I guess, sorry. So actually I was thinking including confounders only. So if we only focused on the outcome models, we would identify variables that are potentially confounders and also the predictor variables. So in that case, that would be, I guess that's, yeah, that could work. I suppose you wouldn't be able to identify which ones are confounders, but as long as you don't need to know that information, you could only fit your outcome model, and then that would use all of those variables. I think that would work.
Okay. Wow. So, Bob, a lot of questions here. Larger variance was theoretically expected for the model, including all effects, but was your results of apparently larger bias also theoretically expected?
Yeah, thanks, Robert, for the question. So, no, it wasn't expected. I think just from looking at the theory behind it, we would expect that the inclusion of selection variables and predictor variables shouldn't contribute to the bias, but the inclusion of confounders is what really affects bias. So I don't think theoretically that was the result that was expected. I do think some of that is probably for RANDs, we haven't identified all of the important variables that need to be adjusted on. And then, Vlad, thanks for your comment about the question from Raphael. So if the outcome model is not correct, then we could be including variables that either are, yeah, I think if the model's misspecified, we might see that we have additional bias. So it's hard to know. It's important to see if you're correctly specifying the model, but also if you've included all the right covariates in the model. So if you have the information needed to reduce the bias.
Okay, we have 1 minute for one more questions, maybe. Yeah, if there's no more questions, let's thank Katherine again for the great presentation, and we really enjoy your talk. Thank you so much.
Yeah, thanks, Anne. Thanks for having me.